Welcome to Heat Transfer. My name is Mr. Mayo and I want to take you through this topic. The document I'm using was prepared and compiled by Mr. Thiongo, a senior head of department in Alliance Girls High School, a very experienced teacher. If you want to reach him, his contacts are here. So this topic about heat transfer, it is mainly we are studying on how heat can move from one region or one place to another. And of course we have three, just like you learned in primary. It is the same concepts, that is the conduction, convection and radiation. We have not changed, but only that now we are seeing the mechanisms in each case. Mechanism in conduction, in convection and in radiation. Before even we move further, I would like us to define what is heat. And as it has been put here very clearly, that heat is a form of energy which flows from one point to another point because of temperature difference, or it's a form of energy that flows as a result of temperature difference. Without temperature difference, there will be no flow of heat. If two bodies are in contact with each other and they are at 60 degrees Celsius each, then the heat will not flow. But if the two of them are in contact with each other and one of them is at 100 degrees Celsius and the other one is at 60, then it will flow from 100 to 60. Why? Because there is a temperature difference. Get that one. Again, I would like us to see the difference between heat and temperature. Heat and temperature, there are many people who actually think they are the same. Heat can cause rise in temperature. Loss of heat, gain of heat can cause rise in temperature. Loss of heat can lead to a loss in temperature. Heat is a form of energy that flows due to temperature difference. Degree of hotness or coldness of a body is what we are calling it now, the temperature. So when you define heat and then you define temperature, it can be used as a difference of the two. So form of energy that flows due to temperature difference, that is heat. Degree of hotness or coldness of a body in some chosen scale. We are going to see that scale. Which one do we use? The SI unit of heat is joules. Joules. The SI unit of heat temperature is Kelvin. Kelvin. Though we have another one in terms of degrees Celsius, yes. But the SI unit is Kelvin. The flow of it cannot be measured precisely. The magnitude of it cannot be measured precisely, but it can be calculated. But we can measure temperature by use of a measuring instrument, that is thermometer. Yes, so those are the difference. Now, having seen that, I would like us to look at now conduction. We will start with conduction. Later on, we will check on convection and radiation. First of all, we have two mechanisms by which heat can be conducted. It is in form of solids. Conduction takes place in solids. The first mechanism is vibration of molecules. Somebody else can tell you vibration of atoms, which is well. Through free electrons. Good. So these free electrons can also be used later on when we shall be talking about conduction of electrical energy. So they participate in thermal conduction and electrical conduction. That is the free electrons. Solids can be classified into two as far as thermal conductivity is concerned. We have good conductors and then we have poor conductors. The other name for poor conductors is insulators. Good conductors are materials that can readily allow heat to pass through them, and we know them. Most of them are metals. Yes, all metals mostly are good conductors of heat, simply because they have the free electrons. So in addition to vibration of the molecules, they also have free electrons. That's why metals are good conductors of heat, and even electricity. Poor conductors, these do not readily allow heat to pass through them. They include wood, air, water, rubber, plastic, glass. Reason being, they don't have free electrons. Yes. So if at You know, when we say poor conductor, it doesn't mean that it cannot conduct. It does, but at a very low rate. So the low way it conducts it is just because of vibration of molecules. Yeah, I think that one is well explained. Solids that are good conductors of it, yeah, because they use both vibration of atoms and free electrons to conduct heat. Yes. While the others which are poor, it's just because of vibration of the atoms alone. There are no free electrons. I want us to look at the factors affecting thermal conductivity. First of all, we start with the type of the material. That is the nature of the material. Metals does so well, and non-metals does not conduct very well. And I think I've given you examples there, up there, on the same. You look at this. It is observed that the wax attached to copper rod drops first, followed by that on aluminium, iron, lead, and that of wood did not drop, since wood is a poor conductor of heat. Yes, just understand in that manner. You see, look at this. This is a wood, and this is okay. It's still you know, we have the wood and we have the iron. All of them connected in the same source of heat, the same source of heat, so that we can compare how iron and wood does so. We cannot use different sources of heat, because somebody will argue and say that the other heat was much hotter than this, but now all of them are put in the same what? Source of heat. A piece of paper is wrapped in the boundary of the two. Then you place them in the source of heat. At the end, what will happen? The part which was on the side of the hood get charred. Charred means it turns black as a result of heat. It almost caught into flames. Why? Because the heat on the side of the hood was not conducted by the hood itself. So all the heat was taken by the paper. But on the side of the iron conducts away heat, and therefore the paper did not get jarred. You hear me, you get me. So that is it, and the explanation is just here. So wood is said to be a poor conductor of heat, while iron is a better conductor. Yes. Temperature difference. Now look at this. The brass, we are using the same material. We are using the same cross-section area, the same length, everything is the same, only different source of heat. Bunsen burner is very hot compared to the boiling water. What will happen in this case? If you have to hold with your hands, you will have to drop the one in Bunsen burner first compared to the one in the hot water. Why? Because temperature difference. If there's a big temperature difference, then heat will move faster. Or if you put wax, the wax will drop faster in the brass rod with the Bunsen burner than with the one in the hot water. Yes. So the rate of flow of heat increases with increase in temperature difference. Good. Let's look at the length of the wire. Conductor, not wire. It's not resistance. So length of the conductor. So you see, we have A and we have B. A, because it's very long, it will take a longer time to conduct it from one end to the other. But B, because it's very short, it conducts it faster to this end. So if you put wax, it will fall faster in B than in A. If you hold with your hands, you will drop the one with B first than the one with A. That is the length of the cross-section. Lastly, cross-section area, that is the thickness. The one that is thick conducts it faster than the one that is thin. So thermal conductivity increases with increase in area of cross-section of the conducting material. The same applies to even conduction of current. It increases with increase in the cross-section area. So let's give you summary. In summary, the rate of heat flow of thermal conductivity increases with increase in temperature difference. That is, the rate of heat flow is directly proportional to the temperature difference. Increases with decrease in length, i.e. the rate of heat flow is inversely proportional to the length of a conductor. Increases with increase in cross-section area. of the material. That is, the rate of heat flow is directly proportional to the area of cross section of the material. Now, lastly, it increases with the thermal conductivity value K of the material. So those are the in summary form about thermal conductivity. This is how it should be. Now I want us to demonstrate that water is a poor conductor of heat. I want us to demonstrate that water is a poor conductor of heat. Look at this diagram, well drawn by Mr. Thiongo. We have the wire gas, we have the ice cube, we have the Bunsen burner being burned at the top. I mean, the water is being heated at the top. And being heated at the top, it will only be boiling. The observation will be the water boils at the top, but the ice cube will never melt. Why? Because water is a poor conductor. You know, if it was a good conductor, it could have conducted water to heat towards the where ice is. Yes. Look at this. Water is a poor conductor. That's what we have said. The test tube is made of glass, first of all, because it's a poor conductor of heat, which limits possible conduction of heat down the tube. Nice. The ice is wrapped in a wire gas to ensure that it does not float. Good. The fact that the wire gas is a good conductor of heat and yet the ice remained unmelted shows that there is a very little heat transfer in the water unable to melt the ice. Even if we are saying that water is a poor conductor, it doesn't mean that it cannot conduct 100%. It does so, but rarely. Water is heated at the top to eliminate possibility of heat transfer to the ice by convection. You know, convection is because of rising currents. So we heat at the top to eliminate or to ensure that the heat does not reach the ice via convection. Yes. Now let's compare between water and mercury. Which one is a good conductor? But remember, mercury is a metal, water is not. So look at this. Asbestos are meant, look at this diagram. Asbestos are meant to shield heat transfer by radiation. Then we have mercury, we have water, we heat. So the copper rod, of course, we use copper rod in both cases. What happens here is heat is transferred to water, and at the same time heat is transferred to what? To mercury at the same rate. The heat that reaches mercury is the same as the heat that reaches where water is. And if that is the case, then it is now the role of water to conduct heat to where the wax is. It is the role of mercury to conduct heat to where the wax is. So what's happening here? The wax in the container containing mercury will melt faster because mercury is a good conductor of heat compared to water. The one for water may not even melt, but if it will take a lot of time. It will take a lot of time. And one of the precaution here is mercury vapor is poisonous. Take care when performing this experiment. Yes. Why liquids are poor conductors of heat? By the way, why liquids are poor conductors of heat? Compare the molecules of liquids and solids. Solids are close to each other, closely packed. In fact, they are touching each other. Look at this. They are not. They are far from each other. So when they vibrate, they are far from each other. So what happens is, by the time one molecule touches the other, it is a lot of heat must have been supplied to it. So that's what makes it to be a poor conductor of heat. You know, they are just close. Now this one explains why now gases are the poorest when it comes to conduction of heat, because the molecules are far away from each other. Somebody is asking me what's the difference between molecules and particles. For now, let it be the same. They stand with the same thing: molecules, particles. Yes. So the large intermolecular distance is what makes liquid to be a poor conductor of heat. Yes. In gases, look at this. He has used Bunsen burner. You know, inside the Bunsen burner we have that region of unburned gases. So you put there a matchstick. It will never ignite. Why? Because yes, we have heat surrounding it. There is heat surrounding the matchstick, but it is a gas, so it cannot transmit heat. It cannot easily burn. And please just look, you pin the matchstick here, and it will not ignite because gases are poor conductors of heat. Very nice. Before we look at convection, where do we apply good and poor conductors of heat? Very fast. Cooking utensils. This one you know at home. If you want to get a sufuria, you will have to use the one that absorbs, or I mean conducts heat faster to where the food is. And if you want to get handles like this one, use a poor conductor so that when food is hot inside, your hands will not burn. Even in buildings, we always put a wall. For example, in this case, we put a, there is walls in two ways. We have, if you want to prevent heat inside from getting out, you put an insulator in between the walls. If you want to prevent also heat outside from getting in, you also put an insulator, so the heat outside will not get in and the heat inside is retained. Yes. That is it. So we have very many applications which I can also challenge you to go and search for more applications. Yes. So continue watching our YouTube channel, Ambassador Foundation, and continue finalizing with this topic in our next video. Kimazana nai angalia next, that takes you through convection and radiation. Have a blessed time.